Hello बच्चों, this is the third lecture of electrostatics, and in today's lecture we will study about relative electrical permittivity or dielectric constant. Next topic will be the Coulomb's law in vector form, then electrostatic force due to system of charges, electric field intensity, and physical significance of electric field. Our first topic is relative electrical permittivity or dielectric constant. Let us know about the permittivity. What is the permittivity? Permittivity is the characteristic of the medium between two static point charges that affects the electrostatic force between them. Let us consider there are 2-point charges Q1 and Q2 separated at a distance r in free space, and the force acting between them is F0. Now let the system is put in a medium in the same situation, that is separated by the same distance r. Now the force acting between them is Fm. It has been observed that the force in medium between the two charges is reduced by some factor k, where k has a constant value for some specific medium. According to that, the force in medium is equal to force acting between the 2-point charges in free space divided by k. This k is also known as relative electrical permittivity, and it is denoted by epsilon r. Therefore, we can write from equation 1 Fm is equal to F0 by epsilon r, or epsilon r is equal to F0 by Fm. That is, we can say that the relative electrical permittivity is the ratio of force acting between the 2-point charges separated by the distance r in free space and the force acting between the same charges separated by the same distance in any medium. Now, according to the Coulomb's law, we can write the value of the two forces. First one is F0, that is force acting between the 2-point charges separated by the distance r in free space, is equal to 1 by 4 pi epsilon naught Q1 Q2 by r square. And the same for the force acting between the two charges separated by the distance r in medium is equal to 1 by 4 pi epsilon m into Q1 Q2 by r square. Here we have considered that epsilon m is the absolute electrical permittivity of the medium, as epsilon naught was the absolute electrical permittivity of the free space. Hence, we can write from the previous equation the value of epsilon r is equal to epsilon m upon epsilon naught. From this equation, we can write the value of absolute electrical permittivity of the medium is equal to absolute electrical permittivity of the free space into relative electrical permittivity. Using the two equation, we can write the electrostatic force acting between the two charges Q1 Q2 separated by the distance r in the medium is equal to 1 by 4 pi epsilon naught epsilon r Q1 Q2 by r square. Epsilon r is also known as dielectric constant. From the previous equation, it is clear that the absolute electrical permittivity of the medium is always greater than the absolute electrical permittivity of the free space, and hence we can say that the force acting between the two charges in medium is always less than the force acting between the two charges in free space. We have studied Coulomb's law in previous lecture, and the law gives the magnitude of the force. Now we will study the Coulomb's law in vector form from which we can get the magnitude as well as direction of the force. According to the Coulomb's law, the magnitude of electric force acting between the 2-point charges is directly proportional to the product of the magnitudes of the charges and inversely proportional to the square of the distance between them. That is, F electrostatic is equal to K into magnitude of Q1 and Q2 divided by R square. Let the expression of Coulomb's law in vector form. Let us consider Q1, Q2 are 2-point charges situated in free space at a distance r. Vector r1 and vector r2 are the position vectors of Q1 and Q2 from the origin O. F12 is the force acting on charge Q1 due to Q2 from B to A, and F21 is the force acting on charge Q2 due to Q1 from A to B. Now we will get the direction as well as magnitude of AB from the vector law of addition. In triangle OAB, vector r1 plus vector r12 is equal to vector r2. From there we get vector r12 is equal to vector r2 minus vector r1. Similarly, we can get the value of vector r21, which is equal to vector r1 minus vector r2. We can write the values of unit vector of the two vectors as unit vector r12 is equal to vector r12 divided by magnitude of vector r12, and unit vector r21 is equal to vector r21 divided by magnitude of vector r21. Now according to the Coulomb's law, the force acting on Q2 due to Q1 is equal to 1 by 4 pi epsilon naught Q1 Q2 by AB square from A to B. Now putting the value of AB from equation number 1, we will get 1 by 4 pi epsilon naught Q1 Q2 by R12 square into unit vector R12. Again putting the value of unit vector from the previous equation, we will get the value of force in vector form 1 by 4 pi epsilon naught Q1 Q2 by R12 cube into vector R12. In the similar way, we can get the value of other vector force, which is F12 is equal to 1 by 4 pi epsilon naught Q1 Q2 by R21 cube into vector R21. The last two equations are the vector form of Coulomb's law. From the figure, we can see that the magnitude of the vector R12 and vector R21 is same, but the direction of them are opposite. Therefore, we can write the unit vector R21 is equal to minus unit vector R12. By putting the value in one of the two last equations of force, we will get F12 is equal to minus F21. And hence we can say that Coulomb's law obeys Newton's third law of motion. Next topic is electrostatic force due to system of charges, or principle of superposition. According to this principle, the force acting on any charge due to a number of charges present around it and all are static is the vector sum of all the forces acting on that charge when the effect of forces are taken individually. That means we are taking the effect of forces on the charge one at a time and ignoring the effect of forces among other charges. Therefore, according to Coulomb's law, we can write the effect of force on charge Q1 due to Q2 is equal to 1 by 4 pi epsilon naught Q1 Q2 upon R12 square R12 cap. Similarly, the force acting on Q1 due to Q3 is equal to 1 by 4 pi epsilon naught Q1 Q3 upon R13 square R13 cap. The resultant of these two forces for the system of three charges will be F1 as shown in figure. Therefore, adding vectorially the two forces, we will get 1 by 4 pi epsilon naught q1 q2 upon r12 square r12 cap plus q1 q3 upon r13 square r13 cap. If there are n number of charges in the system, then the net force acting on q1 will be equal to q1 upon 4 pi epsilon naught summation I is equal to 2 to n qi upon r1i square r1i cap. This is the expression for the electrostatic force due to system of charges. Moving to our next topic, which is electric field. It is the space around a charge in which another charge can experience an electrostatic force. To understand this topic more easily, we will assume the concept of two kinds of charges. First one is the source charge and next is the test charge. Source charge is that which produces electric field, and test charge is to test the effect of that electric field. Therefore, the size of the test charge should be very much small in comparison to the source charge, so that it only observe the effect of source charge, not to affect anything in the field of the source charge. Our next topic is related to the previous one, which is electric field intensity. The field intensity is the measure of strength of the electric field at any point. To determine the expression of the electric field, let us consider 2-point charges, a source charge Q and a test charge Q1 placed at a distance r in free space. The force acting on Q1 due to the source charge Q is F1 is equal to K Q1 upon R square. Now if we replace test charge Q1 by another test charge Q2, the magnitude of force will change, which is equal to K Q2 upon R square. Again replacing the test charge by Q3, we will get F3 is equal to K Q3 upon R square. Comparing the three equations, we get that there is a constant quantity kq by r square in all the three equations for same medium and same separation between the charges. This quantity doesn't depend on the value of the test charge. Hence, we can write the electrostatic force is equal to E into the magnitude of the test charge. That is, F is equal to E into Q. Here, E is equal to kq by r square. This is known as electrostatic field intensity, or in other form we can write E is equal to F by Q. Electrostatic field intensity is a vector quantity and the direction of it is same as that of force. From equation 1, we can define the electric field intensity as electric field intensity at a point is equal to the force experienced by a unit positive charge at the same point. The intensity of the field for a point charge depends on r, and it is inversely proportional to the square of r, as shown in the graph, the variation of E with distance, that is r. At the source charge, the electric field intensity is undefined because for that the R will be equal to 0. Therefore, E will be infinity. Physical significance of electric field. Here the meaning of physical significance is the existence of something. Now to understand the existence of electric field, if we put a test charge near a source charge, it will experience a force. By observation, we can say that there is something around the source charge which is exerting force on the test charge. That is electric field. Electric field has its own existence even if there is no additional charge to experience the force. Your homework is you have to determine the unit of electric field, which I have not mentioned in the previous slide, and you will derive the expression for vector form of electric field and also electric field intensity due to a system of charges, as we have done in previous slide for the force. And last one is the Coulomb's law, its statement and formula.